Now in the last section we want to talk about normal approximation to binomial distributions. Before widespread use of technology, binomial probability calculations were very tedious. Now let's see how statisticians estimated these calculations in the past. Now in this example here it says in 2011 the national premature birth rate was 11.7%. Premature babies are those born more than 3 weeks early. Suppose that 250 live births are randomly selected and that the number X of the preemies is determined. What is the probability that there are between 15 and 30 preemies inclusive? Now let's find this probability using the binomial distribution. Now recall here we have a fixed number of trials, we have a probability of success, 0.117, probability of failure, the complement of that. Each trial is independent of one another, so X can be represented by a discrete binomial distribution. And to calculate that exact probability, the probability that X is between 15 and 30 inclusively, we're going to take a binomial CDF, n, p, x in this case, which is 250, 0.117, probability of success, 30, and that's going to give us a probability that X could be anything from 0 up to 30 inclusively, and then we're going to subtract the binomial CDF, 250, 0.117, 14. We're going to take off 0 through 14 so we can get the probability that X is exactly between 15 and 30. And that binomial probability, if we calculate it, is 0.605. Now we've visited questions like this earlier. However, we want to talk now about normal approximations to binomials. Now, let's first of all, in this binomial distribution, calculate the mean and standard deviation. Recall that the mean for a binomial distribution is n times p. So if I take 250 times 0.117, I would expect to have 29.25 births out of 250 that are premature. The standard deviation is the root of npq. So if I take the square root of 250 times 0.117 times its complement, 0.883, I get a value of 5.082. Now we're going to use those numbers for mean and standard deviation and use those as approximate values for the mean and standard deviation of a normal distribution. Now once again, dealing with the same question here, if we were to graph a histogram of the binomial data, what shape do you think the histogram will have? Recall when we graphed binomial data with different probabilities that we saw that binomial data went from being skewed to the right to being fairly symmetrical at p equals 0.5 to being strongly skewed to the left. Now, if our probability here is 0.117, we would probably assume that we would expect a strong right skew if we were to graph this data. Now, let's graph the distribution for X being binomial with parameter n equals 250 trials, and probability of success is 0.117. Now, to do this, we're going to populate list 1 with X values from 1 to 45. So let's go ahead and use our sequence option to do this. So I'm going to go stat edit. I'm going to jump up to list 1, highlight list 1, and populate list 1 with numbers 1 to 45 by using my sequence option. So I'm going to go second list, right above stat, go over to options. I'm choosing option 5. I'm going to use the random variable X, comma, and I want X, comma, to go from 1, comma, 45. Now, we're not going to populate all of our possible outcomes, which would be 0 to 250. I'm not going to do that. I'm just going to go from 1 to 45. And now, let's go ahead and populate list 2 with the binomial probabilities associated with X having the certain outcomes in list 1. X populate list 2 with binomial probability values. So we're going to use binomial PDF 250, 0.117, list 1. I'm going to highlight list 2, and I'm going to do second distribution. Okay, I'm going to toggle up to binomial PDF. I have 250 fixed trials here. Probability of success is 0.117. And I want how many successes? They're defined by list 1. Exactly 1, exactly 2, so forth and so on. Okay, so it gives me the binomial probabilities associated with X equal those certain values as described.